Hello, greetings and warm welcome to everyone. Myself Manas and along with my project partner Asif are going to give a brief overview on our BTech final year project work. So the title of our project is Specific Lung Region Segmentation-based Pulmonary Disease Classification using GAN and CNN configured in encoder and decoder form. The project is done under the supervision of Professor Kandarpa Kumar Sharma sir and under the co-guidance of Dr. Surajit Deka sir. So here is the outline of our project. I will start with the brief introduction of our project. According to WHO, millions of people get infected with pulmonary disease around the globe each year, and thousands of them fail to survive. Also, historical studies shows that the pulmonary diseases are curable if diagnosed and treated at an early stage. In the recent years, computer-aided diagnostic has been taken place. CAD uses neural networks or deep learning models to provide the results accurately in less amount of time. So that is our motivation to make a deep learning model which can be used to solve image segmentation as well as classification tasks with better performance. Also, our intuition for our method is motivated by the nature of GAN, which generates the realistic images which can be used especially for classification tasks. Here are some of the literature review and comparisons of the techniques we have gone through. And now, the problem formulated was that since interpreting chest X-ray images by the radiologist consumes lots of time and energy, in such scenario, CAD can assist the radiologist by doing trivial processing. The objective of our project is to generate the number of images using GAN. Secondly, segmentation of regions in the CXR images, and at last the classification of images into different classes of pulmonary diseases. The datasets we have used are NIH-CXR datasets, which is publicly available in Kaggle. Here is the overview of the GAN structure. It has two neural networks, generator and the discriminator. Generator's output is connected directly to the discriminator's input. In generator, fully connected hidden layers are replaced by the convolutions. The system model for GAN is shown here. First of all, CXR images are given as input, and in generator, random noise is given. The generated images along with real images are distinguished in the discriminator, giving out the fake images as output samples. And for segmentation of images, unit is used. It is trained on the manual lung mass. In the proposed flow diagram, we can see CXR images and manual lung mass are given to unit to predict the lung mass. These are parameters used for GAN for both discriminator and generator model. Also, parameters used in unit are shown here. The GAN model is trained using set of sample of CXR images. Leaky reactivation function is used. Epoch of 40 is given. Also, learning rate is 2 into 10 to the power minus 4. So the results we have got after training for 40 epochs. The first image is the random noise and the second is the generated fake images. The scores and losses results are plotted here. The base score is 0.7209 at epoch 30 and the maximum loss is 11.5121 at epoch 11. Also, we have shown that comparison table using the different activation functions, the base score and the maximum loss. Here is the segmentation results. When trained for segmentation using UNet, the model has achieved the mean dice score of 0.88 and validation dice score of 0.8764. Also, the IOU score is 0.801 and the statistical results are plotted in the form of graph, the training dice score and the training IOU and the validation dice score and the validation IOU. Here we have shown the results for training loss and validation loss. Also, we have shown the precision and the recall value per epoch. Now for the classification, we have used pre-trained CNN models. The transfer learning approach is used to save the time and computational resources. Here is our system model of the method. The hyperparameters that we have used are grayscale images of size 224 into 224. Batch size is 16. Epoch given is 20. After training our model with different approaches, we have got evaluation results. And VGC19 achieved the highest validation binary accuracy of score 0.929. Also, the results after training with different thresholding is evaluated. VGC16 achieved the highest average accuracy of 0.939. Also, in terms of recall, VGG16 achieved the highest average value of 0.238. These are the accuracy plots for different models. Also, the precision plots are shown here. And again, testing results of VGG16 achieved the lowest testing loss of 0.179 and the highest accuracy of 93.9%. For the AFC score, the values are varied across the model without a consistent performer. Here are the ROC curves of the all proposed models. At last, the model is deployed in a web application using Streamlit library. The last four pictures collectively offer a glimpse into the user interface of the web application. The homepage, disease classification results, and the informative section and the contact details. The UI elements are designed to provide the users with a seamless and informative experience while using the application. So in conclusion, we would expect, for example, another X-ray for every random input to the X-ray generator that we design. Multi-classification techniques are required with the huge dataset for effective, efficient, and accurate detection of various cardiothoracic diseases. Hence, we are aimed to bring the transfer learning in the pre-trained model to use the learning procedures to top deep learning models. Also, the evaluation of segmentation model gradually improves its segmentation accuracy and overlap with the ground truth over the epochs. The precision value is 0.957, the recall value is 0.953, and the loss value is 0.125. The model effectively learned to segment the images and produce accurate results. Comparison of the activation functions, ReLU outperforms the leaky ReLU and ALU with the highest score of 0.97, but incurs a maximum loss. Comparison of the different models in binary classification, MobileNet and MobileNet V2 Inception V3 achieves the higher binary accuracy scores compared to VGG16, VGG19 and Efficient V0. VGG19 achieves the highest validation binary accuracy score of 0.929. VGG19 also has the highest validation precision score of 0.420, indicating a higher ability to correctly identify positive instances. VGG90 emerges as the best model considering accuracy, precision, recall, and AUC. Here are the limitations that we have faced. Since GAN does not allow targeted generation of images, it does not make use of class labels as additional information to improve the image synthesis. In a deep learning-based method, the training of DNNs requires annotated data. If annotation is not properly done, then it will affect the accuracy of the method. The evaluation does not consider computational efficiency or the resources requirements of the model. The future directions are to develop the method for classification of disease using more generated of samples of data from GAN. Also to compare the performance and accuracy using different methods. Further analysis could be included. Exploration of other activation functions or the model architectures could be done to improve performance. Incorporating additional evaluation metrics and considering the trade-offs between them could provide a more comprehensive understanding of the model's performance. And at last, the papers, few of the papers that we have taken as the references. Here is the Gantt chart of our work. Thank you.
Classification task using convolution neural networks for lung diseases. Classification has shown promising results. By utilizing CNN, we can effectively analyze visual data and accurately classify lung diseases based on medical imaging data. The evolution of various pre-trained CNN models such as VGG19 MobileNet version 2 and EfficientNet B0 reveal their effectiveness in achieving high accuracy, precision, recall, and AUC scores. These models have demonstrated their ability to extract relevant features from lung images and make accurate predictions. Streamlit provides a seamless way to display the classification results, making it easy for users to understand and interpret the output. The app can be run locally during development and later deployed to a web server or cloud platform for wider accessibility. Streamlit's simplicity and integration with popular libraries make it a great choice for building web classification apps that deliver a smooth and interactive user experience. The user interface elements are designed to provide users with a seamless and informative experience while using the application. This page represents the homepage of the web application. It prominently displays the name of the application and includes from fields where users can input their gender and age. These fields serve as input for the disease classification or analysis performed by the application. Here, it showcases the results of the disease classification performed by the web application. It displays the classification outcome, indicating the specific disease detected or predicted. Additionally, it also provides the probability or confidence level associated with the classification result. This information helps users understand the likelihood or certainty of the classification. This section of the web application dedicated to providing detailed information about the application itself. The purpose of the section is to provide users with an overview of the application's features, functionality, and benefits. And lastly, this section provides of the web application. It includes relevant information for users to get in touch with the application's administrators or support team. The 4 pages collectively offer a glimpse into the user interface of the web application, covering the homepage, disease classification, results, and informative section and contact details.